Right. Today we're going to do lots more induction. So remember last time I defined induction. Induction is representation. So let me briefly remind you what this was. So maybe I always have subgroup H of group G, find it if you like, and let's say I have U a CH module. So U is a representation of H, a linear, and then I construct it for U. The induction from H to G of U, this is defined to be there's some construction which makes a representation of G starting with representation of H, and sort of you're taking it for yourself U as a vector space, and you're taking a direct sum of U of itself exactly as many times as there are cosets of H and G, and then there's some interesting action on that vector space which does not respect the direct sum decomposition in general. So first business today is to write down the universal property of induction. We'll play with these things. You can be very formal about this, which is in the lecture notes. I thought I would try to give you a less formal account. Let's see if I can do this. So, well, what is the universal property of induction? Well, this is some kind of tensor product. If you knew about non-commuted tensor products, it is a non-commuted tensor product, and so it's universal for a certain balance, that's right, I think, say, maps out of kg times u into somewhere. Okay, that's one thing I'm going to say. So let's say that V be some random kg module, got nothing to do with U in this setup, and say, you see, one thing you can do with it is you can just forget the action of most of the group, remembering only the action of H. You can restrict it to H, and then you can consider HOMs from that restriction into U, the source of the representation. Let for the purpose of consistency with the notes, it's called a W, sorry. Let beta be some AH module homomorphism. So there's some kind of asymmetry here. There's a representation U of H, and then we're varying representations of G, and then we're considering maps from W into the restriction. Did I get this right? No, I didn't. Sorry, let's try again. What is the universal property of induction? I've got my W's and U's switched around, my bad. it better be a W. That's all right. So W, getting there. If I have a KG module, representation of G, I can restrict it to H and I can consider maps from some other KH module into it. And the inverse property is that you can always extend this map in some sense to a map from the induction to W. That's it. Once you sort of think about it in the right way, it's very natural. You can extend maps from U to restriction to the induction. So how? Let me just do the construction. Then we get, there exists a unique beta tilde going from the induction from H to G, U to W, KG linear. Well, it's no good to say that there exists something which is KG linear. Also should be unique, but unique only, you know, with respect to some condition, such that the following diagram commutes. What's that diagram? Well, I've got this map beta, and you see U always maps, as a vector space at least, into the induction what's this? And this U goes to simply 1 tensor bar U. And there's this natural thing you can do. That's it. This statement is the inverse property of induction. I think I've got it right. Shall we prove it? It's not difficult. You just follow your nose. So I need to construct beta tilde. I need to check that it's linear. It's a module homomorphism, G module homomorphism. And then I need to check that it's unique. So, the map from G times U into W, which sends G of my U goes to G dot beta of U, is bilinear. Okay, actually I can put R here, right? R is an element of KG, U is a random vector in U, and beta is a map from of H representations from U to the restriction of a G representation. You see, once I have such a map, I can then remember suddenly that W has a G action and therefore it's a KG module, right? This makes sense. And everything is bilinear. Okay? And so by the inverse property of tensor product, it extends to a K linear map from the tensor product into W, sending the elementary tensor to this. Okay? But the induced representation is not just a tensor product of U with this gigantic, really, thing, it's a quotient of it. So we'll have to just check that it descends to the quotient. So let's see. remember it was the co-invariant, so I have to check that if I do H star do something in here, and that should go to the same place as R tends to U under this. Okay? So what is this? Well, by definition, this is RH inverse tensor H dot U, and this goes to RH inverse dot beta of H dot U, but beta was H, linear, and so the H pops out and cancels the H inverse. And so this computation shows that what shall I call this guy? Beta tilde, beta prime, why not? Beta prime descends or factors through co-invariant with respect to the right action of H on the tensor product. And to give us a well-defined map, which is so far just K-linear map, right? I didn't say what beta dash is. K-linear map. Beta tilde, going from the induced thing, right? That's this thing by definition, into W. So I've constructed the function, and I know it's linear with respect to the ground field, but I'm claiming more. I'm claiming that it's actually G linear, and that's because here, you know, it just is. Check that it is KG linear, beta tilde of group element little g dot something or other in here, maybe R tensor bar U. I think that was my notation for the image of element with tensor R tensor U inside the induced. This is G dot. No, first I have to compute this inside the induced module, then apply beta tilde. Right, so beta tilde of GR, ring product tensor bar U. Beta tilde just acts together with applying beta to the second argument. But nothing's happened, right? This is a module because this is happening inside W, which is a KG module. This is G dot R dot B of beta of U. This is indeed G dot beta tilde of R tensor R U. Shows that therefore beta tilde is KG linear. So, in this setup, given a H module homomorphism beta, I've extended it to a G module homomorphism. It's interesting, right? You get G linear maps out of H linear maps for free by this construction. I've checked that it exists. I better check that the diagonal commutes. We'll do that. Diagonal commute, beta tilde of, if I start that it's a triangle, right? It's only has to be equal to beta. Take something in here, then if I go this way, I have to take 1. Well, I've got a formula for beta tilde. It's just act, right? 1 dot beta of U, 1 doesn't do anything in any module over a unital ring. It's unital, so indeed the diagonal commutes. And finally, why is it unique? Suppose there was some other beast, beta double dash or something, such that diagonal commutes and it was linear. It's another kg modular morphism, making the diagonal commute, beta double dashed of 1 tensor bar u is equal to beta of u, all u in u. I claim that beta double dash is equal to beta tilde, and that's because it's linear, and it agrees on the generators. And the point is that in the induced representation, U generates the induction as a G module, that construction. It's a big generator. Then beta double dash of R tensor bar U, or any R in kg. Because it's linear, you see this is how the group ring acts on the induced module. And since it's linear, beta double dash, I can pull it out, pull the R out. Okay, and then by assumption, beta double dash of 1 tensor bar u is just beta of u. It's R of beta of u. Right, but that's beta tilde of u because I've checked that it works. Oops. So this is true for all R kg, for all u in u, and these images of elementary tensors span the induced representation. Not careful, not equal, not everything is equal to something like that span. But both things are. So if you've got two linear maps which agree in a spanning set, then they're equal. So it's absolutely unique, subject to these conditions. Did you like that universal property? I think it's better than the proposition. The proposition is a formalization of this universal property. I think what do we prove? Let's prove proposition 6.10 in notes. Says that there exists an isomorphism, or bijection at least, from the space of H linear morphisms from W into the restriction. That's where we started, right? U's and W's completely mixed up, haven't I? I'm so sorry. See if I get this right. Yeah, I got the U's and W's mixed up. Never mind. This is correct. The inverse is correct. There is a bijection from this set, right, to every beta in here. There corresponds a unique kg linear map from U, from the induction of U into W. Right? So the setup is exactly as in this board. Sending beta to beta tilde. Right? It exists. It's unique. And I think well, okay, so I'm claiming that this is bijection with inverse. If I have something in here, alpha goes to alpha composed with the map, sends U to 1 tensor bar U. Okay. So how much of this have I actually proved? I've proved that beta tilde exists and is kg linear. I've proved that if I do this operation to beta tilde, I get beta, that's the commutativity of this triangle. I've proved that it's unique. I suppose I haven't proved that it's surjective. But it's obvious it's surjective, because this is generated, right, by the image of U under this map. Okay, so let's just check that it says everything. We have to check injectivity, and the surjectivity of this. Suppose, say I have an alpha in the right-hand side, which is a G-linear map from the induction. Then necessarily alpha of alpha is a beta tilde, right? Alpha of G dot tensor by U by linearity is G dot alpha 1 tensor by U. But you see, this thing here is actually H linear, so really I could have put a restriction of the induction back down to H here. This map here is a homomorphism of H modules. How does H act on this? H dot 1 tensor bar U is H tensor bar U. But I can move H across as long as it's in H. That was lemma 6.5. 1 tensor bar H U. And this guy here is a homomorphism of H representations. And therefore, this is an admissible beta, right? G dot beta U. Whoops. Yeah, so that's beta tilde of G tensor bar U, where beta is this composition. I can't fall U, can I? That's a disaster. Okay, that's fine. Right, and this function really is, for easy reasons, in the left-hand side. Okay, so every alpha is a beta tilde pattern. Good. So, and maybe as an exercise, check that this thing is actually linear, because these spaces are more than just sets, right? They actually are vector spaces. So everything is linear. And it's better than that, it's even functorial if you start messing around with U's and W's. You can allow yourself to move U to U prime and W to W prime and write down some commutative diagrams until you're blue in the face of everything. It's a nice bijection. Okay, this is called the junction. Okay, in module representation here. An important proposition. If you read the notes, we're very, very formal. I'm not going to write them out. It's the universal property of it. Good, so other stuff we're going to do today is we're going to compute characters of induced representations. So I'll get to go very quickly, otherwise I'll run out of time. So I'm going to skip definition 611, which says that I use notation restriction induction for characters. Okay, the restriction of a character is simply the restriction of a character. The induction of a character is the character of induced representation afforded by the character you started with. Really good. So, this is what are they called for the name Frobenius reciprocity. Frobenius reciprocity is what you get if you take the tensor homotopy, so this adjunction thing, this bijection you take, you recognize that these Hom spaces encode, in particular, inner products in character values. Remember? That was in the proof of row orthogonality. And so we'll take dimensions of these vector spaces, we'll get inner products of various characters. And so that's what Frobenius reciprocity is. It's an equality of two different kinds of inner products. There are two different inner products actually in play, because I've got two groups, G and H. So I've got two different class function spaces, C of H and C of G. And so for characters, phi be character H, psi be a character G, then induction is left adjoint to restriction. That's how you remember it. I'm even going to make this precise. It's not just a slogan, but actually true. Okay, is it clear what this means? No? Phi was a character of H. Therefore, it was the trace function of some representation of H, some KH module. I induced it after a representation of G, called int HG of carrying space. I took its trace. That's what this is. Okay, this is an object in the space of class functions on G as psi because it was a character of some representation of G. I take the inner product. Okay? And the claim is the same as phi. I can also get, instead, take the inner product of phi with the restriction for H of the character. Statement clear? Okay. Left-hand side is equal to, by proposition 522, to the dimension of the space of CG HOMs in HG of, oh, I better put U here, and I better put W here so that this comes in play, right, consistent with that. Right, phi is afforded by W, lovely English word, afforded by W, you will not find it in other countries. By U. Okay, and then this is by this exercise, the linearity that most of these two vector spaces have the same dimension. Suddenly K became C because otherwise I can't apply 522. That required some C in the coefficients, right? And so the proof is complete. Apply 522 again. I get right hand side. So I'm just observing the character of the restriction is equal to the restriction of the characters. So you're just taking the trace of the restriction. Any questions about Frobenius reciprocity? Maybe skip the example 613, just maybe tell you what the example is. Induction from the trivial character. We know what this is, I think. I take U to be a simple CH module. Right. G module. H is the trivial group, sorry. One. Well, by Frobenius reciprocity, this is in the product 1 with restriction. u, what is that? That's just the value of the character 1, that's h, which is the trivial group. Which is the dimension of u. And so that tells us that u, any simple, well, I think we simple. But if u is simple, if u is simple, then it follows that u is CG, the free CG modular rank 1 in u times. Point being that sometimes you might be interested in computing this count value. Of course, this is just the group ring, right? CG. This. If you induce that from the trivial representation of the trivial group, you get the group ring. Okay? How many times does U appear in the group ring? If U is simple, it's computed by this infinite. And so this is a non-trivial statement. Right? That follows already from Martin Wedderburn. When U, any simple module or finite group appears in the group ring exactly as many times as the dimension of that. Good. So now character of induced representation. So unfortunately, it's a difficult calculation. If you look at the invariant way of writing down what the character of an induced representation is, you find that it involves a very elegant sum and an extension by zero function, which we'll get to shortly. But the proof goes through this calculation, which I'm going to do first and foremost. But this is a very important lemma, which where we're going to see how, roughly speaking, the matrix representation of the associated to a natural basis of the induced representation looks like. What do I mean by natural? I've got this induced thing, which is a direct sum of some number of copies of u, the thing I started inducing from. And so I pick a basis for the induced thing, which respects this decomposition of vector spaces. And then the statement is that the action of the big group permutes for blocks about. And the matrices are all block form. That's what we're going to see in this lemma. And then we'll be able to just read off the trace. Okay. So, morally, the content of this lemma is that, provided you've chosen your basis correctly, the matrix of the value under the induced representation of a group element is in block form. You can read off from the one of these blocks the in the. I better do the left. Okay, so where do these blocks come from? They come from this coset decomposition that we've had before. Right? So everything's finite. We can find the complete set of coset representatives x1 up to xm for h and g. And I fix little g and g. And now already, the permutation action of g on the set of cosets is interesting. Right? So I'm going to have some notation for that. GXIH. What's that? Well, that's a coset of H, right? So it must be exactly one of these cosets. This coset contains exactly one of the x's. Don't know which one. So I'm going to write that. Right? So this is a, as the French would say, transport a structure. Transport a structure from the action of G on the coset space to the set 1 to M. It's permutation representation. For all I going from 1 to M. Okay. And then I'm interested in the fixed point set of this action. So I'm interested only in those numbers I where little g is fixing I. So it will turn out that the trace of the action of little g on the induced representation only depends on this set. So let W be a finite dimensional CH module. So finally I switch to the nodes. Then the following things happen. First of all, G sends this block, or this direct command of induced, into the corresponding direct command, commutes this command in this precise way. And moreover, you can compute therefore the character of the induced representation, or as a character theorist will say, you can compute the induced character at G by means of the following formula. Make the sum over all fixed points of little g on the indices of the character values of what? Well, chi w is a function on h, so I have to feed into it. It's an element of h. But fortunately, I is fixed by g, so g dot I equals I. That being the case, gxi is in xih, and so xi inverse gxi is in h. And that's it.
Is like A actually an equality?
It is an equality if I don't need that. It's an equality by the usual argument replacing g with g inverse. Okay, so that's a statement. So it's part A, which is somehow the nice description of the group action on the induced representation. It's in block 4 in this precise way. So you should not be scared of induced representations. They're completely accessible to computations. You can write down matrix representations if you have enough board space. Trouble with matrix representations that you usually H has a large index in G, and W, the source representation, is usually large. So if you have anything non-trivial, you usually have a 4x4 matrix, and that's already too many entries for me. Just make do this. Okay. So I better prove A, and this is just completely obvious. Indeed. Definition of group action. And at this point, this G wants to push past the tensor. I can't quite do that, but I have notation, fortunately. Right? The trick here is that GXI does lie in xg.ih, right? Because this is 1. And 1 is in H. Yeah, so I can just take the inverse. Nothing's happened so far, except to observe that this group element is in H by construction. Okay. If I move this to the left, I get something in H. And things in H, you can move past the tensor product. That's lemma 6.5 last time. This is a complicated group element in H, depending on everything. But at least it's in H. That's good news. Because then this makes sense. Yeah, so what's happened? G moved this elementary thing to another elementary thing where the index has changed in a predictable way, and you can even compute what this is if you want. Any questions? Now trace. We have to compute the trace of the matrix. So, importantly, this is a direct sum again. Let me just record that. We have this decomposition as vector spaces. And A says that the action of little g on the induced module emits these direct sums. So we'll do a little example maybe. Suppose it was the case that g.1 equals 2 and g.2 equals 1. What's going to happen to your matrix? Pick a basis for u, then you get a basis for the induced in the obvious way. Right? Then, if this is true, you're going to have something in here, actually the action of, what is it? X g.1 inverse gx1. That's some random element. Well, actually, this is 2, right? This thing is then with H acting on W. It's going to have some matrix here. Right? So actually, the matrix of this. Well, I don't have a name for the representation, right? You know what I mean, right? The matrix of this linear operator on W goes into this corner. That's what this computation trails. Likewise, the matrix of what happens to the other block, well, that's when I is 2, and g.2 is 1, so I have x1 inverse gx2 here. This is an element of H. It has some action on W. I take the matrix of that endomorphism. And that's it. There's nothing else here, big fat zeros. Right? So when I is not fixed by little g, I get no contribution in the trace. That's why fixed I appears. Okay? It's really difficult to make this completely precise so that ChatGPT or something can check it. You read Sarah's book, you just say, yeah, it's okay. That's the best you're going to get from here. Right. So the important point is that only the indices which are fixed by our little g matter in the computation of trace. Right. And those are polys, right? So, the trace of the restriction the action of G on the induced module to a fixed block in the case when I is fixed by G, and in that case alone, otherwise the statement doesn't make any sense, is phi part A of this lemma equal to the trace of the action of x g dot I inverse g x I from W. That's what you're going to get in the block form. And that's what's appearing in the formula. Take traces. Okay? So the proof is complete. Any questions? No? Good. So let's do one more calculation now. So this lemma tells us what's going on. You better understand this lemma. If you don't understand this lemma, then you're going to have trouble with characters and induced representations. Okay? But I think we do understand the lemma. It's an important lemma. The objection to this lemma is that it is not invariant. There is a choice right at the start of the lemma. Yes?
Is there a mistake in B? Because chi is a class function, so the conjugation there doesn't do anything. So should it be
Exactly the point. You see,
G dot
I is fixed by G. G dot I equals I. And so xi is equal to x of g dot I.
Yes. So why not throw away the conjugation?
Hmm?
Calculating the character in G and calculating W.
Are you happy with this sentence?
Oh, because it has to be in W.
Yeah.
Alright.
Okay. Right, so now I'm going to write down the invariant version of 614, which does not depend on the choice of a cursive representative. Sorry, HG. There's this notation called extension by zero. Of some function defined on H. So it is what you think it is, right? It's phi on H and 0 no, on H. That notation is the invariant form of trace, so the induced character. So notation as before. The value of the induced character of a representation of H called W on a group element little g is sum over all elements in the group. It's a funny formula, but completely standard, I'm afraid, of conjugates of the element G. So it is invariant, right? No choice is made. Makes sense? Okay. This was a function on H, but I extended it by 0, and I'm feeding into random conjugates of the element little g. And typically, right, so you can already see here that the conjugacy class of little g, right? Little g is the fixed parameter here, and h is going to appear a lot when you apply this formula, because it's only for these things you're going to get non-zero contributions. And in general, this thing is something random. The only thing I can say about this, in my state of knowledge, is that it's a union of h conjugacy classes. Right? Obviously, this is a single g conjugacy class, therefore it's stable under conjugation by h. This is stable under conjugation by h, therefore the intersection is also stable under conjugation by h, therefore this is a union of h conjugacy classes. But that's maybe for the next lecture. Let's prove this and take a break. I'm going to multiply everything by mod h and compute, work backwards. So work out mod h times the right hand side. Mod h times the right hand side is sum x and g extension by 0 for character of w and the x conjugate of g. Now, obviously, I need to apply the previous lemma 614, which requires choosing a complete set of closest representatives for h and g. And then I split up this sum according to its decomposition. So, substitute x equals xi h. Sum to get something or other. Well, inverse is reverse order. That's that. There's a g here. Oops. So far, so good. Okay. Chi w was an h-class function, therefore its extension by 0 is also an h-class function, namely it's stable under conjugation by h. So the h goes away. And so the inside of the sum, h does not matter at all, but I'm still doing the sum mod h times. And I want this to be mod h times the left-hand side, but I put lemma 614 for the left-hand side. Right, that's here. Oh, look, it's basically the same. Mod h pulls out. And so the last thing I have to do is just observe that if I is not fixed by the action, then this thing is actually not in h, and therefore when I apply the extension by 0 function I get 0. And in this case, the 0 function can be dropped because it's just a character. So finally I apply lemma 614. B find that's equal to h times the character induced representation of little g. I'm going to cancel my okay. Let's take a break.
Sorry, sorry. Professor. So why do we need I fixed G? I didn't
Yeah. Because that was so the line is scanner.
Yeah, exactly. I didn't get that. Why do we need I fixed G? So that xi equals xi is h.
Because xi inverse g xi is an h. If and only.
Oh yeah, that makes sense.
Right, I'm going to restart. Finish induction today. said already, but it's important. So let's write it down. You have this group theoretic relation between the subgroup H I'm inducing from and the conjugacy class of element whose character value on the induced representation I want to compute. Then actually that character value is automatically 0 for any H modulo W, right? Because there's just no fixed points of the actual G on the tensor product. The block matrix is no non-zero diagonal matrix. Oops. Right. There was this invariant thing which I dropped off. Apologies. The way to remember the formula is in terms of the slogan. The slogan is induction. Is adjoint. Left adjoint if you're so minded. Restriction. We'll make this precise. If you don't know any category theory, you might decide that adjoint means something to do with inner products and linear maps. We have a linear map, right? Restriction. I have a class function on G, and I just restrict it to H. The resulting function is stable under conjugation by H, right? Every intersection of H with any conjugacy class is, again, the union of H conjugacy classes. This is a well-defined function. This is both inner product spaces. With respect to the standard O2 style norms. Complex inner product spaces. So I want to, in order to, that was one of those favorite linear algebra questions, wasn't it? Let T from U to V be a linear map between complex inner product spaces. Show that the adjoint is well defined and unique. It exists, right? What is it? It's induction. So, you didn't know anything about tensor products or covariance or that funny construction, but you only knew character theory as presented 2 weeks ago, and restriction, you might have posed this question, what is the adjoint? I think maybe possibly Frobenius and his friends in the 19th century did it this way, actually. Right? Consider this question, what is the adjoint to restriction? And you can actually compute it group theoretically. So I will, I'm afraid, define it. Write it out of the hat. Define the map in the other way, and I will show that it satisfies the functional equation that witnesses that this function, which I'm about to define, is the adjoint of restriction. You see, on this level, there are no representations inside; they're just class functions. It's the same formula. Right? claim that this makes sense and is linear. Right? And again, that's obvious. It makes sense is because I've extended by 0. This is well defined. And then the corollary is that scatter. But you see, we're going to prove it using representation theory. I think it's a nice exercise in just messing around with double and triple sums over the loop to actually prove this corollary directly, because the statement makes sense without any reference to characters. What's the statement? I take a class function on H, induce it up in this sense, and take the G in a product of some class function on G, and that's the same as taking the inner product of the function on H with the restriction of the function on G. So this really does say that this induction function is adjoint to the restriction. Well, you might be scratching your head saying, haven't I done this already? I've done this for characters, haven't I? True. We have 5 is a character of H, some H modulo W, and psi. U some H module W and CG module U, sorry. This is by Frobenius reciprocity. Together this formula is the character of the induced representation. So we're done. Because characters span. Irreducible characters span. Right? Any class function can be written as a C-linear combination of irreducible characters. You can even be precise about these scalars, right? Between products. J. Notation sucks. J down to IR, some random scalars, don't care what they are. Well, you just stick it in. and you get a double sum on both sides. It reduces to the case like that. Substitute result. Right. So next there is a well, I'm going to do what else we're going to do. I'm going to simplify the formula for the character of induced representation, and I'm going to examine the case when the subgroup I'm inducing from is normal, and then I'm going to compute the character table of the dihedral group, and all in 40 minutes. Right, I better get on with it. So, the problem with this formula is it's very elegant, but it involves this annoying circle, which you don't really know how to compute maybe, and you probably don't fancy computing this over all elements of the group and then seeing whether or not you're an H and then computing the character. It's not a bit unwieldy, right? So we're going to write down a more efficient way of phrasing this definition. So to do that, first, so fix little g and g. It's all about the character of induced representation. The value of the character on the fixed element little g, and h as that we of g as before. So obviously, the intersection of the conjugacy class of little g with the subgroup h is important in this formula. All we know about this set is that it's a union of h conjugacy classes. Everything is finite, so I can choose a complete set of representatives for the conjugacy classes that appear in this intersection. This is the hard group theoretic part, maybe. If you know the character of your representation you're inducing, your representation of the subgroup, then you maybe know what the values on the H values are. So the formula simply is in terms of it's a weighted sum of those character values. Okay? I challenge you to remember it. Whatever I'm inducing, I think this probably works for any class function. I don't care about representations. So the point of this corollary is that you don't have to sum over all elements of G, it suffices to sum over 1 to L. To do that, there are some weights involved. Not an obvious formula, I think. I think it's clear that some such formula exists, because obviously this function is either 0 or constant on these H conjugacy classes, so it's clear it's going to be some linear combination of these values, but which one? It's exactly this one. So, how to compute this? Let's work backwards again. No, let's work with the definition. The definition is this one here. obviously the sum of elements in G, right? So most of those elements, well, not most, some of them are going to be giving us 0, and some not. So let's just focus on those which contribute, where S is those elements in G. Whoops, well, my G's and X's switched around, that's a disaster. Sorry. So I want X inverse GX line H. I define that obviously this set is important in view of this theorem, 616. And equally obviously there's going to be a lot of repetition. Right? This set is fibered over H. There is a function from this set into H. Little g is fixed. I don't know really what to call it. Something. Tau S H sends X to X inverse G X. Can't argue, right? And if I have, you know, some set, some smaller set, and I have values for a function called kw circ. Actually, I can drop the circ here, right? By introducing recess, I can drop the circ. Anyway, obviously this depends only on the tau, right? And that being the case, I can split up the sum into fibers of this function tau. Some y in the image of S, full fiber size, chi w y. Begs the question, what is this fiber and what's the image of S? Well, the image of S, I think, is obviously this intersection we started with. Oh, where's it gone? Right. This is the image of tau, isn't it? It's tau of S. And we'll have this notation. We can further split this up into bits. Like this. So it really just comes down to the size of each fiber. Okay, and that's the different thing. So now let's compute the size of the fiber. Well, fix y in tau of S maybe, when is something else in the fiber of y, then disaster. Maybe y prime is in the fiber of y. Well, this is computable, right? If and only if, and right, y is tau of some group element called x naught. Tau has a precise definition, it's conjugation, right? It's not really conjugation because g is fixed. It's a funny function. by the inverse and right multiplied by b. Anyway, so that being the case, y is in here if and only if tau y primed equals tau of y. The definition of tau says that y primed y primed x, sorry. There we go, I'm getting there. So far so good. You can solve this equation. So do centralize it with the g. Isn't group theory fun? And this equation has a different meaning. This is saying that the difference between 1 Good. So the conclusion is, hence, this proves that the map from the centralizer to the full preimage of the image of some element x naught, there you go, sending something like this, I don't know, z to z x naught is a bijection. Because anything in here, any x which tau maps to tau of x naught, has to have the property that this difference, this centralizes. That's why it's significant. Good. And therefore, all of these fibers have the same size. Not quite. So hence, sum I equals 1 to L tau inverse I W H I I screwed up there. This is not right. Because I've only taken representatives. Right? Actually, I want to count all of the elements of a conjugacy class here. That's better. Anyway, this one's just a centralizer of G. And using orbit stabilizer, I can get rid of centralizer by replacing it by this. And the mod G goes away, and I start applying left multiplied by mod H. So that's going to go in the denominator. That's it. Good. Okay. I need to press on. So this is is a nice formula if you can remember it, because it helps you to compute induced characters as an algorithm, right? All you have to do is compute this, compute these sizes, compute everything, and then bingo. Right, so now normal subgroups. Assume I've got a normal subgroup. In this case, and look back again at the action of the group element in G on the induced module, I remember it was commuting the various direct sums, various summands in the induced module, precisely as how the group element little g was permuting the cosets of H and G. I've got a normal subgroup. This action is trivial. In this case. G X I N is equal to G X I G inverse G N So what I said was wrong. I'm sorry. Things simplified. The character formula simplified a lot. But I have to start with an element of age. You see, in the formula before, I wasn't even guaranteed that elements of age preserve blocks. The block matrix you get the action of even the end of the subgroup you started with might not be block diagonal, but in the case of the normal subgroup it is. H, Xi, N is Xi, Xi. Inverse HXI, N, but H is an N, and N is normal. So this is an N, because N is normal, and so it goes away. So that means that's permutation. H in N on the cosets. Then G. Completely trivial because this is a group, and trivial of this factors through N. So hence, H N on the induced H dot G is logged down. But better than that, again, H isn't little H isn't big N. Actually, you can actually see what it's doing. If you go back to lemma 614, I think it was, I computed what this was. Right, this is using this calculation here. This is an N subgroup, and so I can move it across. right? So not only is a block diagonal, but you can actually even tell what H is doing for each block. And it's not just H acting on the block, it's a twist. Whoops. Right, you have to conjugate H by something or other, and then we look back. Okay. So this motivates the following definition. Normal subgroup. Okay. X, B, and G, and let phi be a function of n call the X twist function I get by precomposing phi by conjugation of n by x, which is a well-defined thing because it's normal. Well-defined because conjugation phi, any elliptical group reserves. Maybe G is Sn and N is An. Maybe X is like an odd combination. You will get something, right? Conjugate. And even implementation by not one, you might get different, something which is not An conjugate to what you started with, right? So the actual implementation action on the conjugacy classes of N may well be non-trivial. Restricts and automorphism. Group automorphism. N automorphisms preserve conjugacy. Classes. N, and hence G times C of N is actually, a well-defined group action. Right, I'm saying that if phi is a class function in N and I twist it by some random element G, I get another class function, and this operation gives me a group action of G on the set of class functions. Furthermore, observe that if x happens to be in N, then phi x is phi, because phi is already stable in this action. Factors G1n. That's phi x of h equals phi x inverse x equals phi of h. For all h in n, if x happens to be in n as well, right? Take something in n and twist your class function in n. This is all general nonsense. Nice things you can do. You have a normal subgroup, n, g, we have top group and quotient group. You have class functions N and G, but then acts on the class function. General nonsense. Good. And so the rest follows, I think, very easily. Have to just get used to this formula. Okay? Because I've done the hard work. I've told you how random elements of the big group act on the induced representation, and they were acting in a way that commuted the direct semantic composition of the induced representation in a controlled way. So what I'm interested in this proposition is to compute the restriction to n of an induced representation, right? And this is very nice. If n is normal, and I'm only interested in the action of n itself on the induced and actually only the character, right? Then you get a nice formula. So, first of all the twists phi be your character of some n representation. Then, if I twist the character by a group element. Again, a character. Of some Cn module. This operation is definitely non-trivial. And furthermore, back to my original notation, cosines of the subgroup in the group, and then the character induced as a function is the sum of twists. Obvious, right? I've done the proof. The proof was motivating the twist step. Here's the proof. Right. Like a restriction. Doesn't make sense otherwise. If I put the restriction here, this is a character of G, and this is a sum of twists of characters of W, this is a function of N. Right? The restriction of the induction is the sum of twists. There you go. So maybe briefly, why is A true? What is this? Twisted module you just pre-compose, right? For A, let Wx dW as a C vector space. But define n action, linear action. N action by n dot W equals, well, U action, right, depending on x. What do I want? Let's send this one. Conjugate by x, that's an automorphism of the group, and then I apply my representation. Right? This is well defined because n is normal and x is fixed. And then the trace obviously will be normal. Okay. And B I've done here. really good because I can now apply Frobenius reciprocity to compute the character of an induced representation from a normal subgroup. And this is an application of induction. Sometimes you will get lucky and your induced character is irreducible. You can use Frobenius reciprocity to prove this. Here's the criterion of what lucky might mean. So say n is normal and phi the character of some representation of n, which is irreducible. Suppose just all the characters are reducible. And second of all, the G mod n orbit of that character in the space of class function of an n is a copy of G mod n. Right? As you move the character around, you don't get any repetitions. Same thing. If all the twists of the irreducible character are different, then the induced representation is irreducible. Well, this is very nice, and the proof is very easy, because I use, first of all, I use the general theory. It's enough to show that the induced character has norm 1, right? Any character of a representation of the group G decomposes after Marschke as a sum of characters, finite sum of characters of irreducible representations, and furthermore, the norm square of your character is the sum squares of the multiplicities. You want to show it's actually equal to 1, so it's enough to do that. It's enough to show that the multiplicity, exactly one irreducible piece appears with multiplicity 1, and all the other ones are 0. You can read that off from the norm square, but norm square is an inner product, right? To which we can apply Frobenius reciprocity. Frobenius reciprocity tells me I can move the induction from the left and replace its restriction with the right. That's nice and easy and formal. But now you are left wondering what this is. Fortunately, I've done this already. This is the sum of the twists. By 513. X1 and XM, these are the twists with the usual notation. Right, that was the last thing I proved. E621, and this one was Frobenius reciprocity. Finally, I assumed the two things about my character. It was irreducible, and the distinct twists are different. Well, two different characters have 0 in the product. They're pairwise orthogonal, right? So this sum collapses to just the first one. This is by the second assumption. Log x1 is 1. And using the second assumption of this is just 1. The phi was irreducible, and so this is 1 again by some other version.
are characters.
I'm assuming this condition.
Yeah, but if it's not equal to phi, why does it necessarily have a zero inner product with phi? If phi x is not phi, why is that?
Because I assume that phi is irreducible, and the twist of an irreducible character is an irreducible character.
Yeah, but why is the twist of an irreducible character still irreducible?
You're right, I did not say it, but it is true.
Okay. Okay.
Do you now see it?
I don't see
Shall we prove it? Take a subspace, a G-stable subspace of this twisted character. Think about the action. Mhm. It's true. Because a subspace under the twist, I mean, basically, you see, the way the twist works is you fix an element of the big group. You're applying, I mean, more generally, if you have an automorphism of your group N, and you have an irreducible representation, you twist it, you still have an irreducible representation, right? Because the action in the twisted representation of any element of the subgroup is equal to the value of the morphism of the element applied to the vector in your candidate invariant subspace. And so you thus see that a subspace is invariant for the original action if it was invariant for the twisted action. Yeah? And there aren't any. Thank you. Out of time. Am I? No? All right. That's 622. So that's a good character. So this is an application of induction, right? We want to complete our character tables as a criterion. If you have a normal subgroup and some irreducible character which satisfies this condition, which is a proper condition, will not be satisfied always. Okay? But it is sometimes satisfied and it's very useful. Sometimes induced characters are irreducible. So that's the case of dihedral groups. Let's compute the character of the dihedral group, the odd dihedral group. Example. There are not enough examples. This is an example, but that does not alleviate the fact that there aren't enough examples. I apologize. 16 lectures. Okay, dihedral group. Odd dihedral group, which means it has order. I mean, any dihedral group has even order, but maybe it's a symmetry group of a regular GON, which has an odd number of things. So I write it like this: dihedral group order, that order. Okay, so it has a presentation, has a rotation, and the reflection. The rotation has order precisely 2m plus 1. The reflection has order 2, so order reflection 2. And furthermore, if you take the rotation and you conjugate it by your reflection, you will get the inverse reflection. That's your presentation for the dihedral group. So the conjugation action of S on the normal subgroup is a non-trivial automorphism on this cyclic subgroup of order 2m plus 1, given by negation if you identify your cyclic subgroup order 2 solventitious model. Dihedral group. Good. So very simple group, meta-abelian. It's an extension of the abelian group on top, and all metacyclic in class 2. So we know exactly what the character theory of N is. N is abelian. N is, of course, rotations. Cyclic group of order 2m plus 1. All characters are linear by an exercise you did. There are exactly 2m plus 1 characters. Actually, characters form a group under multiplication of an abelian group. So it's again cyclic. Anyway, so the characters, the reducible characters of N are necessarily of the form trivial, and powers of one kind of fundamental character where you fix some primitive 2m plus 1 through to unity in C, and you send R to that thing, and you call that character a name. And then all the characters are powers of this guy, calling it phi. Phi Rj is omega to the j. Omega is e to the 2 pi I over 2m plus 1. Complex number. Right, so then there's this twisted action, right? I told you, for general reasons, the conjugation action of G on the normal subgroup N is by a group homomorphisms respecting conjugacy classes, therefore passes to this set, to a permutation action with a set of conjugacy classes of N, and therefore by functionality of functions passes to an action on the space of class functions on N. I can twist the class function on N by an element of G. Here, G mod N is just a copy of C2, right? Generated by the image of S, cyclic of order 2. How does this act? On the set of irreducible characters of N? Well, you can just compute, right? Phi to the I, that's like an irreducible character. I can twist it, and then I can ask myself what that's doing to an element of the group. Actually, it's enough to do it on the generator, because once I know what this character is doing to a generator, I can then identify the character. I is a non-negative integer, S is a group element. Conflict notation. Okay. Anyway, by definition of twist, it's this, but conjugation by S inverts R. And these are actual group homomorphisms because they're linear characters of degree 1, so I can pull out the inverse. And phi to the I sends R to omega to the I, then I have to invert it, and so this is equal to I to minus I, working mod 1 plus 1, obviously. So therefore, phi to the I of S is equal to phi to the minus I. Mod 2m plus 1. Good. And so we see that the G mod N action fixes the trivial character when I is 0, it's minus 0, 0, and the other ones are in pairs. And therefore the condition of the corollary holds, right? If I take a non-trivial character of this cyclic subgroup order 2m plus 1, then its S is not equal to itself, and therefore the induced thing is automatically reducible. So in this way, I will get lots of, for free, two-dimensional reducible representations. Gives how many? 2m plus 1 is the number of irreducible characters of n. Take away 1, which is fixed by the S action, divided by 2, which is m, and irreducible characters of G or m plus 2 of degree 2. Okay. Am I supposed to compute anything else here? I think I'm now supposed to say that's it. There aren't any others. Why aren't there any others? I mean, you can even compute their formulas, right? Because I told you how to compute the induced character. Nearly done. How can I tell if I've got enough characters? First of all, they're all different, right? If the characters are like the restriction n to G to the induction, phi I is phi I plus phi to the minus I, right? And this shows that the these inductions are different if the pair II inverse is not equal to the pair JJ inverse. Yeah, because the restrictions are already different functions. So I will have m degree 2 things. Just add up the degrees. So I have m degree 2 things. I have to square the degrees. That's 4 q squared times m. And how many linear characters are there? 2. Well, that's 2. There it is. It's the size of d to m plus 2. Why, therefore, linear? So the derived group, right? The number of linear characters is the derived group index. And here it's 2 because you can compute for yourself the derived group is generated by R. And if you compute the combination of R and S, you get R inverse.